Right. So this is my amplifier. Okay. So for this, I have to draw the Miller equivalent circuit. Okay. The feedback resistances. First, it is 1 mega ohm. Then the second case, it is 1 picofarad. Both the cases, I have to find what is my gain, overall gain of the system. Correct. And remember, AV which is given, that is gain of the amplifier alone. So AV here is actually V naught by Vi, not V naught by V signal. So I have to find what is V naught by V signal for both these cases. Right. So if I draw the equivalent circuit, okay, so if I draw the equivalent circuit, so this is plus minus V signal. This is R signal. And here I'm replacing the Z, okay, with say this here is Z1. Okay. Then at the output side, I have a dependent source. Okay, I have a dependent. This source will actually tell me it is minus 100 times VA. Okay, remember this is VA. Okay, now I have here Z2, Z2, then finally VA. Right. So here I know Z1 is Z divided by 1 minus K. Okay, and Z2 here is Z divided by 1 minus 1 by K. Remember, K here is AV. Okay, so first bit, if Z is 1 mega ohm, okay, if Z is 1 mega ohm, then Z1 is 1 mega divided by 1 minus of minus 1. So it is simply 9.9. Okay. Similarly, Z2 you have, which is 1 mega divided by 1 minus of 1 divided by minus 1. Okay, so this will give me 0.99. Okay, you can do the calculations on that. I will share this with you. Right. So for this, what is V naught by V signal? Okay, so V naught by V signal is actually V naught by Vi into Vi by V signal, where I can write V naught by Vi as AV, okay, which is minus N2. And if you look at this circuit, okay, R signal and Z1 are actually a voltage divider configuration. So I can write Vi as V signal divided by Z1 plus R signal into Z1. All right. So with this equation, I will write this here. Okay. So this is AV into R Z1 divided by Z1 plus R signal. So substitute all the values. So this is minus 100. Z1 is how much? 9.9 kilo. So this is 9.9 kilo divided by Z1 9.9 kilo plus R signal. R signal is 10 kilo. So the gain here is minus 49. Okay, minus 49.7 volts per volt. So V naught by V signal when you're having Z as 1 mega ohm is minus 49.7. right? Now, okay. Now for the second part, where z is now 1 picofarad. Okay, z is now 1 picofarad. So I will write this as z1 is equal to, again obviously it is z by 1 minus k. K is AV, remember. So z I will write as 1 by SC divided by 1 minus k. So 1 minus k is minus 100. Okay, so this will actually turn out to be 1 by S into 101C, where C is 1 picofarad. It is given in the question. This one. Okay, Z is 1 picofarad. Right. So again, Z2. Okay, let me look at Z2, which is Z by 1 minus 1 by 2 is 1 by SC divided by 1 minus 1 divided by minus 100. Okay, so this will actually give me 1 by S into 1.01K. Okay, so where again C is 1 picofarad. 1 picofarad. Okay, so this is done. So Z1, Z2 I have found. Right, you can substitute the value of C and still, but your equation which you get, okay, the value of Z1 which you get, okay, it will be in terms of S sum, right? And if you exactly want what capacitances you use, then you can write Z1 as 1 by SC1 equals to 1 by S into 101C. So from this, I will know that C1 is actually 101 picofarad. Okay. And similarly, Z2, I can write it as 1 by SC2, which is 1 by SC into 1.01K. Okay, this I can write as C2 is 1.01 into 10 power 3 picofarads. Okay, so these are the actual C1 and C2 values. Now, if I look at the gain part, okay, okay, V0 by V6. Okay, we have written this as minus 100 into Z1 divided by Z1 plus RC. Okay, if you look at the previous one. This one. Right. So here I will write it as this. I will write it as minus 100 into Z1. I will write it as, I can't write Z1. Remember, I can't write Z1 as 101 picofarad. It is wrong. I have to write Z1 as this. Okay. So 1 divided by C into 101C divided by 1 divided by S into 101C plus R signal. R signal is 10 kilometers. Right? So if you solve for this, you should get V0 by V signal as minus 100 divided by 1 plus 101 1.01 into 10 power minus 6 into S. Okay. So 1.01 into 10 power minus 6 into S. So this is actually a transfer function. It's actually a transfer function. Okay. Transfer function with a gain of 100 minus 100 and a 3 dB frequency here. And the 3 dB frequency here, 1 divided by 1.01 into 10 power minus 6 radians per second. Okay, how I got this is, if you remember your transfer function, okay, transfer function, generally, transfer function is written in this f of s is equal to gain divided by 1 plus s divided by omega naught. Okay, this omega naught is actually a pole, right? Actually a pole. So this system has only one pole. So obviously that will be your frequency, cutoff frequency. So here for this omega h, cutoff frequency will be actually omega naught. Okay, cutoff 3 dB will be actually omega naught. So therefore f 3 dB or fh, okay, it is 1 by 2 pi. See, it is in radians per second. I can't keep it in radians per second, right? So I have to write it in kilohertz or in hertz. So into 1.01 into 10 power minus 6. So this will finally turn out to be 157.6 kilohertz. Right. So this, so I can say that on a final note, I can say that so it is a transfer function. Okay, a transfer function with a gain of minus 100 and 3 dB frequency of 157.6 kilohertz. Okay, this happens only if C is your Miller capacitance. Okay, instead of having a feedback resistor, you have a capacitance. Only if C is present, capacitance is present. Okay. So it is a transfer function. It's a transfer function which has a gain of 1000, minus 100, and a 3 dB frequency, 157.6 kilohertz. Okay. So this is your problem. Any queries in this? Any queries in today's class? So we started with recap. We saw some inferences of the previous problem. Okay, but what is the trade-off between gain and lambda? And then we saw what is Miller's theorem. Okay, derived it. What is Z1? What is Z2? And if I replace the Z with the capacitance, okay, I will have to put a capacitance which is multiplied by the factor of 1 minus k at the input side and multiplied by a factor of 1 minus 1 by k at the output side. Right? Similar derivations, then we saw a problem. Now I have applied the same concept to the problem. I'll try and go through this problem once again. If you have any queries, do let me know. Okay. I'll see you in the next class.